Here's a lesson on negative exponents. In part 1 of this lesson, I'm going to teach you the negative exponent rule by simplifying this expression in two different ways. We'll start by writing this quotient of powers in expanded form and then simplifying. So I'll zoom in here on this quotient, and I'll rewrite it in expanded form by changing a to the power of 4 to 4 factors of a being multiplied together, and a to the power of 6 as 6 factors of a. And since a divided by a is 1, I could cancel that pair of factors. And I could also cancel 3 more pairs of a's that are being divided by themselves, which leaves us with in the denominator 2 factors of a. So in the denominator of our simplified expression, there will be an a squared. And in the numerator, since those 4 factors of a divided by those 4 factors of a is 1, in the numerator, we have a 1. And now let's go ahead and simplify that same expression, but this time, we'll use the quotient of powers rule, which states when dividing two powers with the same base, which we have here, we have an a to the power of 4 divided by an a to the power of 6, what we do is we keep that same base of a and subtract the exponents, 4 minus 6. And 4 minus 6 is negative 2, so this equals a to the negative 2. And now what we've discovered is that a to the power of 4 divided by a to the power of 6 is equal to both 1 over a squared and a to the power of negative 2, which tells us that a to the power of negative 2 must be equal to 1 over a squared. And notice, if I took the reciprocal of a to the power of negative 2 and changed the sign of the exponent, I would get 1 over a squared. So that's going to be our negative exponent rule. The rule says, when raising a base to a negative power, so let's say we have a to the power of negative m, this would equal its reciprocal with the sign of the exponent change. So it'd be 1 over a to the power of positive m. And now let's practice that rule in example 1. Example 1 says simplify each expression by writing it as a power without a negative exponent, and then evaluate if possible. Starting with part A, 5 to the power of negative 2, I could rewrite that as the reciprocal of that power raised to a positive exponent. So 1 over 5 to the power of positive 2, which equals 1 over 25. And then in part B, 4 to the power of negative 3, I set that equal to its reciprocal with the sign of the exponent change. So it'd be 1 over 4 to the power of positive 3. And 4 to the power of 3 is 4 times 4 times 4, which is 64. So this equals 1 over 64. Then moving on to part C and part D. In part C, I have a quotient of powers that have the same base. I can combine those to a single power by keeping that base of x and subtracting their exponents, 5 minus 9. So this is equal to x to the power of negative 4, which with a positive exponent, I write it equal to the reciprocal of that power with the sign of the exponent changed to positive 4. So it becomes 1 over x to the power of positive 4. And then for part D, I have a base raised to a negative exponent. I can change the sign of that exponent by writing it as 1 over that power where I keep the base the same, 2m squared, but I change the sign of the exponent, making it positive 3. And now I can use my power of a product rule, which tells me this exponent of 3 has to be applied to both factors of the base, the 2 and the m squared. So this would equal 1 over 2 cubed and m squared cubed. And then to finish off the simplifying, 2 cubed is 8. M to the power of 2 to the power of 3, using the power of a power rule, I multiply those exponents, giving me m to the 2 times 3, which is m to the power of 6, giving me a final answer of 1 over 8m to the power of 6. And now let's look at what happens when the base of our power is a fraction and the exponent is negative. We'll learn a little bit of a shortcut. So for this power here, a over b to the power of negative 3, if we apply the power of a quotient rule, I know this exponent of negative 3 has to be applied to both the a and the b, making this equal to a to the negative 3 over b to the negative 3. And then using the negative exponent rule, I can rewrite both of these with positive exponents if I write the reciprocals and then change the sign of the exponent. So a to the negative 3 becomes 1 over a to the positive 3, and b to the power of negative 3 becomes 1 over b to the power of positive 3. And now I have a fraction divided by a fraction. We can use the keep, change, flip rule, which says we can rewrite the quotient of two fractions as a multiplication by keeping the fraction that's in the numerator and multiplying it by the reciprocal of the fraction that's in the denominator. So multiplying it by the flip of that, which would be b cubed over 1. And in case you don't know, the reason why we're able to do this keep, change, flip, really what we did was we multiplied top and bottom of this fraction by the reciprocal of 1 over b cubed. So we multiplied the top and bottom by b cubed over 1. And anything divided by itself is 1, so we're really just multiplying by 1. So we're not changing its value. But what happens is this 1 over b cubed will cancel out exactly with this b cubed over 1. That equals 1, leaving us with this product in the numerator, which is exactly what I wrote here. And then to simplify that product, I multiply the numerators. 1 times b cubed is b cubed, and a cubed times 1 is a cubed, so the denominator is just a cubed. And if I make a bit more room, if I were to then again apply the power of a quotient rule, I could rewrite this as b over a all to the power of positive 3. So notice what happened between the original statement and the final answer. Well, the base of the power, that quotient of a over b, just flipped to b over a. And the exponent went from negative 3 to positive 3. So we can use that shortcut whenever we want. So the negative exponent rule with a rational base, let's say we have a over b to the power of negative m, I can rewrite that equivalently by taking the reciprocal of the base, so flip it, and then change the sign of the exponent. So from negative m, it becomes positive m. And let's see if we can practice this rule in example 2. Example 2 says simplify each expression by writing it as a power without a negative exponent, then evaluate if possible. So when we have a negative exponent on a rational base, like here we have 3 over 4 to the power of negative 2, I can rewrite that with a positive exponent by writing the reciprocal of the base. So flip it, making it 4 over 3, and then change the sign of the exponent to positive. And then to evaluate this, I'll use my power of a quotient rule, which tells me that exponent of 2 goes on both the 4 and the 3, making this 4 squared over 3 squared, which is 16 over 9. For part B, I have a negative exponent on a rational base, so I can make this exponent positive if I write the reciprocal of the base. So change the base from y over 4, change it to 4 over y, and then make the exponent positive 3. And then using the power of a quotient rule, I change this to 4 cubed over y cubed, which is 64 over y cubed. And now moving on to part C. Once again, negative exponent on a rational base. So I flip the base, and then change the sign of the exponent, making it positive 4. Then use my power of a quotient rule, which tells me to put that 4 on both the numerator and denominator. And then in the numerator and denominator, I have a power of a power. With a power of a power, so for y to the 9 to the power of 4, I keep that base of y and then multiply the exponents, making it y to the power of 9 times 4, which is 36, divided by x to the power of 7 to the power of 4, I keep the base of x, and then multiply the exponents 7 times 4, making this x to the power of 28. And then because the bases of these powers are different, I can't simplify this any further. This would be my final answer. And now let's move on to the last section of the lesson, where we try and simplify some expressions that involve all of the exponent rules learned throughout this unit. So let's start by filling out this table as a refresher of what you should know. If you have a product of powers that have the same base, so for example, a to the power of m times a to the power of n, you keep that base of a and add the exponents m plus n. But if you have a quotient of powers with the same base, so a to the power of m divided by a to the power of n, you keep the base of a and subtract the exponents m minus n. And if you have a power of a power, so a to the power of m raised to the power of n, you keep the base of a and multiply the exponents m times n. For a power of a product, if the base of the power is a product of two factors like a times b, and the exponent is m, you raise both factors of the base, both the a and the b, to the power of m. And the power of a quotient rule is similar. If the base of the power is a quotient, let's say a over b, raised to the power of m, that m goes as the exponent on both the a and the b. The zero exponent rule tells us that anything to the power of 0 is equal to 1 as long as a itself is not 0. And the negative exponent rule, which we practiced in this lesson, tells us that a to the power of negative m is equal to its reciprocal with the sign of the exponent changed. So it equals 1 over a to the power of positive m. And if you have a negative exponent with a rational base, so let's say a over b to the power of negative m, that's equal to the reciprocal of the base, b over a, with the sign of the exponent changed to positive m. And now let's use all of those rules to simplify these final three expressions. Starting with part A, I have a quotient that I can simplify. I'll start by dividing the constant factors. 12 divided by 4 is equal to 3. And then I'll look for powers that have the same base and see how I can combine them to a single power. I have a k to the power of 2 being divided by a k to the power of 5. Using the quotient rule of powers, I know that's equal to k to the power of 2 minus 5. And then I have two powers of m being divided, so I can write those as a single power by keeping that base of m and subtracting their exponents, 8 minus 5. Simplifying those subtractions, I have 3 times k to the negative 3 times m to the positive 3. And a fully simplified final answer should not involve a negative exponent. So I'm going to have to rewrite this power that has a negative exponent. I'll change that k to the negative 3. I'll rewrite it with a positive exponent by writing its reciprocal, 1 over k to the power of positive 3. And then when you have a product of whole numbers and fractions, the whole numbers, remember, are actually over 1. So when multiplying this, these whole numbers just multiply into the numerator. So our numerator becomes 3 times 1 times m cubed, which is 3m cubed. And in the denominator, we just have k cubed. So often what I like to think of to simplify this expression, when I'm at this step right here, let me actually make a bit of room. I like to think of that expression as a fraction over 1. And then what I can do is take any powers that have a negative exponent. So for example, that k to the negative 3. You can take that power and move it to the bottom of the fraction, and that just changes the sign of the exponent. Notice in the denominator of our final answer, we have that k to the power of positive 3, and in the numerator, we have 3m cubed, which is what's left up in the numerator on that step. So when simplifying future expressions, we can use that trick. Let's go ahead and do part B and part C. Part B, in the numerator, I see I have a product that can be simplified. I have a constant factor of 5 times a constant factor of 4. That's equal to 20. And I have two powers of c being multiplied together. Using the product of powers rule, I can simplify those to a single power by keeping that base of c and adding their exponents, 3 plus 2, which is 5. And then I also have two powers of d being multiplied together. I have a d to the power of 1 being multiplied by a d to the power of 2. Writing those as a single power, I keep the base of d and add their exponents, 1 plus 2, which is equal to 3. And then in the denominator, I have a power of a product. This 2 has to be applied as the exponent to all factors of the base, the 2, the c squared, and the d, giving me 2 squared, which is 4, and then c squared squared, and d squared. And this c squared squared, using the power of a power rule, I can multiply the exponents, making it c to the power of 4. And now I can simplify my quotient by doing my divisions. I have a 20 divided by 4, which is 5. I have two powers of c being divided. Using the quotient of powers rule, I'll keep the base of c and subtract the exponents, 5 minus 4, which equals 1. And when the exponent is 1, you don't actually have to write it. And then I have two powers of d being divided. I can keep that base of d and subtract their exponents. 3 minus 2 is also 1, giving me a final answer of 5cd. And then moving on to part C, I have two fractions being multiplied. So I'll start by multiplying the numerators. When multiplying the numerators, I can combine these constant factors, 2 times 5, to give me 10. And then I have two powers of x being multiplied. Since they have the same base, I can simplify them into a single power by keeping that same base and adding their exponents, 2 plus negative 6, which is negative 4. And then I also have a power of y and a power of z. Since they have different bases, I can't combine them into a single power, so I'll just leave them. And then in the denominator, I have a 7 times 3, which is 21. And then again, I have a power of y and a power of z being multiplied. Since they're different bases, I'll have to leave them as separate powers. And now at this step, I can look to divide any powers that have the same base to simplify this expression. The constant factors, 10 over 21, that fraction does not simplify, so I'll leave that fraction of 10 over 21. This is the only power of x, so I'll leave it. There are two powers of y being divided. Using the quotient of powers rule, I could combine them into a single power by keeping that base of y and subtracting their exponents, -4 minus 3, which is -7. And then the two powers of z being divided, I'll combine them into a single power by keeping the base of z and subtracting their exponents, 6 minus -3, which is 9. And then we don't want a final answer with negative exponents. So both of these powers that have a negative exponent, I can change the exponents to positive if I write the reciprocals of the powers. And now to get my final answer, it may help to think of that z to the power of 9 as being a fraction over 1. And then the numerator, I have 10 times 1 times 1 times z to the 9. That's 10z to the 9. And in the denominator, I have 21 x to the 4 y to the 7 times 1. And that's the final answer. Another way we could have gotten to that same final answer, let me erase a little bit of what we've done. When I did all my dividing to get these quotients, I could have written all of these powers up in the numerator with the 10. And then I could have taken the powers that have the negative exponents, the x to the -4 and y to the -7. I could have taken each of those powers and moved them down to the denominator to change the sign of their exponents, which notice is the same final answer. And now let's move on to part D. In part D, I'm going to start by simplifying this power of a product. This exponent of 3 has to be applied to both the 2 and the m to the -4. I'll leave the numerator the same and apply that power of a product rule in the denominator to give me 2 cubed and an m to the -4 cubed. I'll leave the numerator for now, and in the denominator, 2 cubed is 8, and then I can simplify this power of a power by keeping the base of m and multiplying the exponents. -4 times 3 is -12. And now I can simplify this quotient by first simplifying the constant factors. 2 divided by 8, I can reduce that. 2 over 8 reduces to 1 over 4, and these powers of m being divided can be combined into a single power by using the quotient of powers rule, which tells me keep that base of m and subtract the exponents, -4 minus -12, which is 8. So the final answer can be written like that, 1/4 m to the 8, or we could move that m to the 8 up in the numerator with the 1, giving me a final answer of m to the 8 over 4. And now let's do our last example of the lesson. Let's do part E. I notice I have two powers with rational bases where their exponents are negative. So I can use the rule that tells me I can change both of those exponents to positive if I flip the bases. And if the exponent on a power is 1, we don't have to write that. And then based on the power of a product and power of a quotient rule, this exponent of 2 has to be applied to all factors of the base, the 10, the y to the 4, the z to the -1, the 3, and the x to the -2. When I apply it to the 10, 10 squared is 100. And when I apply it to the y to the 4, multiplying the exponents because of the power of a power rule, I get y to the 4 times 2, which is 8. Applying it to the z to the -1 would give me z to the -1 times 2, which is z to the -2. And then in the denominator, I have to do 3 squared, which is 9, and x to the -2 squared, which is x to the -4. And then also remember, when dividing fractions, we can change the operation to multiplication if I flip this second fraction. And now I'll do my multiplications to simplify this further. In the numerator, I have 100 times 8, which is 800. I have a power of x being multiplied by a power of y. They're different bases, so I'll just leave them. But I also have two powers of z being multiplied together. To combine them to a single power, I'll keep the base of z and add their exponents, -2 plus 2, which is 0. And based on the 0 exponent rule, z to the power of 0 is 1. And I don't need to write any constant factors of 1. And then in the denominator, I have 9 times 15, which is 135. And I also have this power of x times that power of y. And now to finish off this question, I just have to simplify this quotient. 800 divided by 135. Well, 5 goes into both of those numbers. It goes into 800 160 times, and it goes into 135 27 times. So that fraction reduces to 160 over 27. and then dividing these powers of x. Using the quotient of powers rule, I keep the base of x and subtract the exponents, -5 minus -4, which is -1. And dividing the powers of y. As a single power, I keep the base of y and subtract their exponents, 8 minus 2, which is 6. And when finding the quotients, these variables could have been written up in the numerator with the 160. But our final answer shouldn't have a negative exponent, so we take the power that has the negative exponent and move it down to the denominator, so the sign of its exponent changes to +1, giving us a final answer of 160 y to the power of 6 being divided by 27 x to the power of +1. So there's the final answer. If you made it to the end of the lesson, hopefully you fully understand all of the exponent rules from this unit now, and make sure you go to jensenmath.ca so you can get a copy of the practice questions to practice simplifying expressions using exponent rules.
Jensen Math.